Hello, welcome to video 22 in the lecture Advanced Mathematic Modeling. So now, since in the last video we discussed multivariate distributions and covariances, we now finally can enter stochastic processes, so that are random numbers which depend in time. So what is a stochastic process? So now we want to model stochastic events which evolve in time, so we want really to have dynamics. So now we have a temporal sequence of random numbers. So our random number x at time t1, x at time t2, and so on until x at some time ti. Now, in the same way that we can have distributions which are discrete and continuous, also here the time can be either discrete, so we can have a discrete sequence of random numbers. We can also have a continuum of random numbers, so to every real valued time variable we associate a random number, but keep it in the moment for discrete time events. And now, since we have these random numbers, and the random numbers are given from a distribution, then our distribution depends on the time point. So we have a distribution of the random number, but this distribution in general is not a constant, but this is a distribution which depends on time. And sometimes we write it like p of x and t. Sometimes I forget the order of x and t, which variable is the random number and which is time. But usually you see it from the symbol, so t is always time and x the random variable. Maybe sometimes I write it as p of t and x. Yeah? I should be consistent, but sometimes because authors use it differently, and sometimes I mix this up. Anyway, if we have random numbers which depend on time, given by a time-dependent probability distribution, we have a stochastic process. And now it is so that if we have this distribution, we have solved our problem. But very often, in order to obtain this, we have first to find the solution. And from the problem, we get just some increment of the change of probabilities. So, you know, like in the form in models, when we have a deterministic model, we want to so the model is just given as a change of the state variable in time. This is, for example, x plus x of t plus a function of x. Yeah? So the model gives us the change of the state with time, and when we solve the model, then we get our state for all times. So the model is a change, and the solution is the dependence for all time points. Yeah? And the problem to solve a model is to go from the difference equation to the full solution. And something similar we have here also. If we would have this time dependence of the probability distribution, we have more or less solved our system. But very often we just have a joint distribution. This means we have the distribution that our random number has value x1 at time point t1, and it has the value x2 at time point t2. So it's a multivariate distribution of our random number at different time instances. Yeah? So that's really a multivariate distribution. And this, when we have this multivariate distribution, then sometimes we can calculate the full time dependence. And that's why I introduced multivariate distributions in the last lecture, and now in the last video, and now we can use everything we had in the last video and apply it to a random variable which changes in time. So first we can look what's statistical independence. Let's say we can write this multivariate distribution P of x1, t1, x2, tu2. We can write this as a product of the marginal distributions times P of x2, t2. Yeah. And that's important, t1 not equal t2. We're speaking now about different time instances. Yeah. If we can separate this as a product of the marginal distributions, we call this process an independent process. And if this is not the case, here, then we say the random numbers are dependent. So that's the first. So now we can calculate moments. So that's the definition as before. Now we can calculate moments. And what moments do we calculate? So first, what's the expectation value? That's now a function which depends on time. So the expectation value of x, which depends on time. You see, sometimes I write the time dependence as here as a function. Sometimes I write an index. It's just a different notation. And so what is this? So the expectation value we need to integrate over the x. And then we have x times our probability distribution for x. Yeah? And so that's the. So this means if we have expectation values like the moments, or these are functions of time. In a similar way, we can calculate here such a expectation value of x at time point t1 multiplied at x at time point t2. Yeah. And this is, as usual, defined. We integrate over d1, x1, we integrate over x2, x1, x2, and the joint distribution p of x1, t1, and x2, t2. Yeah. Yeah, it was just visible. So like that was just a way to calculate here moments. But then we have seen also in the last lecture, but this is not really the fundamental moment that we are the moment or the most fundamental property or object that we are interested. We are usually interested in the covariance. So how does this look here when we apply it for time-dependent random numbers? So, and this we give it a special symbol. We often call this kappa, which depends on two time instances, t1 and t2. And that's now the covariance of these two, the random number at different time instances. So that's, we have x at time point t2 minus expectation of x at t2. We close the parenthesis here and we multiply this by x of t1 minus the expectation from x of t1, and from the whole thing the expectation value. So that's just the covariance of x t1 and x at time t2. So the covariance of our random variables at different time instances. And we have also seen we can rewrite this a little bit different, so we can also write this as the expectation value of x at time point t2 times x at time point t1 minus the product of the mean values x at time point t2 times x at time point t1. Yeah? So the covariance of our random variable at two selected time instances. Okay. And so this we call the covariance function. Sometimes people also call it the auto-covariance function, because it's the covariance of a variable with itself, only to different time instances. So that's auto-covariance function. Sometimes we also speak about the auto-correlation function. Even though we know for the correlation we should normalize this by the standard deviations, but often standard deviations are 1, for example, or we don't care so much. And very often, so people use autocorrelation function, but sometimes we mean the autocovariance function. And this word auto, sometimes it's not used, and we just say covariance function. Whatever is whatever term we use, that's the thing we are interested in. That's the fundamental quantity to describe the time dependence of the random variables. And this function gives us the memory of our process. Because this tells us how our random number x at a future time point is correlates to the random number at an earlier time point. Yeah? So in principle we would need this full joint distribution, but very often we are happy if we just have this covariance function. So now the most simple case that is possible is that we have this independence. Yeah? Let's assume our process, we have independent random numbers in different time points. Independence. Yeah. Then we know for independent random number the covariance is 0. Yeah. So this means this kappa of t1 and t2 equals 0, but only if t1 is not equal t2. Yeah. But if t1 equals t2, then we have here the same time points. This means we have the same variable here, and then this is just the variance of x if t1 equals t2. So the most simple case is that we have this independence, and but then we have always to be careful. Do we speak about different time instances or the same? If we have different time instances, and since we don't have memory, this covariance is 0. But if we have the same time instance, yeah, then we have the same random variable, and then this is just the variance of x. Yeah? So this covariance function is then a function which really depends if these time instances are different or identical. So the next thing that we can look for, which makes cases a bit more simple, is if we have stationary processes. So in a strict sense, a stationary process means, so let's first write in a strict sense, it means that our probability distribution does not depend on time. So this means we still have a sequence of random numbers. We still have a process which evolves in time, but the probability distribution doesn't care about this. At every time point we have the same probability distribution. Yeah? So that means, like, for example, if we take a repeated throw of a dice, so at every time point we take the same dice, we get a sequence of random numbers, but it's always from the same distribution. That would be stationary. Sometimes stationary is used in a weak sense. And that means that we don't know what's happening with the probability distribution, but we know something about the moments. And for the moments, stationary means, let's write it down. Let's say we have a moment of variable x at time point t1 times x at time point t2, and then maybe x at time point tn. Yeah, and then we say this moment of x at different time points doesn't depend on the absolute time. Yeah, it just depends on the time difference between the selected time points. So this means if we would shift the time, then this would be the same as if we take x at t1 minus tau times x at time t2 minus tau and x at time tn minus tau. So this means the absolute time point doesn't play a role, but only the relative times between the different time points that we have here. So we can say the absolute time doesn't play a role. And only the time differences are important. So now, what does this mean for some moments? First, I mean, it's clear when we have stationary process in the strict sense, then we have also stationarity in the weak sense. I mean, that you can show easily. So now let's speak only about stationary in the weak sense. What does it mean for example, the moment, the expectation? What's the expectation of x? And so now if you can shift the time as whatever we want, this means this is actually a constant. So even in a weak stationary process, our mean value does not change in time. So now what happens with our correlation function kappa at t1 and t2, and then we have now these moments at different time points, but since we can shift the time, so these moments just depend on the time difference. So this is actually a function which depends on the absolute value of the time difference between the variables. And we call this very often here the time difference tau. So this is just a function which depends on the single variable tau. So here stationary means, of course, when we go in the future, the random variables in the future differ from the random variables before, but it only depends how far we go in the future. It doesn't matter what's the absolute value. And this means the autocorrelation function is just a function of a single variable, and this can be plotted. So here if we have time and we have our correlation function, so it's just a function which starts at a certain value and then changes in time. And then we will be interested to see, and that's why it's called autocorrelation or the autocovariance function, because then it's just a function of the time. Oh well, sorry, here now you see it. So it's just a function of the time difference which can be plotted. Autocovariance function. And so usually, if we don't say anything else, we always assume we have stationary processes, at least in the weak sense. Then the autocovariance can be expressed as a function of a single variable, and so we have here this function. And that's then the function which describes the memory in our system, because it tells us how random variables at a certain time are related to random variables at some arbitrary different time. And this can change. They can be in future time, you might sometimes be positively correlated, negatively correlated, positively correlated, and very often in the very far future this dampens. So there is no correlation, because when you go in a million years in the future, this will be independent from the value of your random variable right now. So that's, and the way how fast this function here decays tells you how strong the memory in the system is. So if we have a stationary process, we can characterize the memory by this function for different time instances. Now let's come back to this here. If we now have independent random numbers, then we said this kappa is either 0 or equals to the variance, depending if the time points were different or equal. So now what's happening if we have independent and stationary random numbers? And then we say, typically we say we have independent and identical distributed numbers, independent and identical. Identical means it's stationary because at every time we have the same distribution, and independent means we want that the covariance is 0 for different time instances. And that's the most trivial stochastic process we can have, and this is often described as IID for independent, identical, distributed. We have an IID process. That's the most simple thing that we can have. And what does the covariance function look like? If you see this, now we can use the delta function which I introduced you before, because this kappa depends, since we are stationary, only on the time difference. And we can say this kappa of tau equals the variance of x times a delta function of tau. And so now the delta function becomes important. So if the time difference is 0, the covariance function is we have the variance, and if tau is not different from 0, we go to 0. So this now would be a autocovariance function kappa of tau, which for 0 has a certain value. So that's the variance at point 0, and then the rest for all other values, this kappa is 0. So it's a function, it's just a delta function. We have only covariance for the same point, but then it's always 0. So basically that's no memory. The function directly decayed to 0 for the fastest, for the smallest time difference. So when we said in general the autocovariance function is a function which decays, and the time it needs to decay gives us the memory. If we don't have a memory, then for infinitesimal small tau, the covariance is reduced to 0. So a system without memory, and this means every time point we have just the same distributions. Random variables at different time steps are not related at all. Very often we have also that the mean variable, the mean of the random variable is 0. Yeah, because like if we have stationary distribution, we have seen where do we have it? If we have a stationary, the mean value is a constant. Then we can normalize everything so that the mean variable mean value is 0. Then here everything is more simple because we don't have to subtract the mean values. So we just have the covariance is just here this product, and so the covariance is just described by x at time t prime times x at time t. Now I have written it as t and t prime. Before I had x1 and x2, and so we have here the variance sigma squared times a delta function of t minus t prime. And a process which has this, and this is basically equivalent to this what we had before, only that we normalize the mean to 0. We call such a process, we say this is a white noise. That's the simplest process without memory. Autocovariance is a delta function, and then we subtract so that the mean is 0. And so that's always like when we have a process where we at different time points always take this random numbers from the same distribution. And now the thing is, how can we find and characterize stochastic processes which differ from this, where we have some memory in the system? That will now be the challenge for our next videos. So, but for now we have now introduced all fundamental concepts. We have stochastic processes, and now we can start to go to hopefully interesting examples. Thank you.